Hi, thank you for inviting me to give a keynote at this great new venue. Today, I'm going to talk to you about the GraphIt Universal Graph Framework, achieving high performance across algorithms, graph types, and architectures. As you know, graphs are everywhere. From social networks to ride-hailing apps to web search to even mobile payments, a lot of these applications are built on top of graphs. These graphs can be very large, and getting high performance is very important either by processing billions of edges and nodes or having very tight latency requirements to do the processing. But when you look around the computing world, for the last 50 years, we have built a world that is mainly focusing on dense computations, from hardware to software. So if you look at hardware today, the microprocessors and GPUs are amazing. They get really good performance on things like dense matrix multiply. They do this by building really interesting innovative features from an entire cache hierarchy to branch predictions and prefetching. These systems are developed over many years and they work extremely well. From the programming systems also, we have done many things for dense application, from building the right abstractions and a slew of libraries, and also optimizing compilers. Starting from the Fortran compiler, we have focused on how to get really good performance for dense applications. But when you look at graphs or sparse applications, that's not the case. This hardware that's built for dense applications perform very poorly when you are going for sparse applications. For example, if you look at application like PageRank, it has really bad cache utilization. More than 40% of memory accesses are cache misses, compared to almost nothing for dense matrix multiply. So because of this, you get really bad performance and bad utilization. When you look at programming systems, to get a high performance graph application is really hard. You have to write very complicated code. Only ninja programmers are able to achieve that. And this is even worse because there's no one graph application that fits all. Graphs, the data of the graphs can be very different, from social networks to meshes to traffic graphs, and many different graphs has very different formats. And of course, there are hundreds of different algorithms you want to perform, and you want to run this on different architectures too. So today in my talk, I'm going to talk about three components. First, I will talk about how to get better hardware utilization using current generation hardware, how some optimizations can do. Then I'm going to talk about the GraphIt domain-specific language and compiler to show how we were able to get uniformly good performance on large class of applications using this system. And finally, I'm going to talk a little bit about hardware to see how a single DSL can target multiple hardware and get good performance. Let's start by looking at basically hardware utilization and how to get good performance. So I'm going to start with a simple application that most of you probably know, PageRank. So let me explain this very briefly. PageRank basically iterate over the graph. So first, it will visit all the vertices of the graph and go to its neighbors and basically updates its rank by looking at the rank of the neighbors. And then it basically create a new rank by looking at the old rank and the new calculated rank, and then basically do the rank swap in that. So the last two computations are done by node, and the first computation is basically has to be done across nodes, go through the edges for the neighbors. So let's look at the memory characteristics of this program, especially this computation. To do it simply, I'm going to look at a graph of basically 4 vertices. And we are going to represent this graph using a CSR format. So you have vertex array and edge array. And the vertex array points to the start of the edges for that vertex. And this is the right representation in the CSR array. And if you look at this axis, new rank, it will basically go linearly through this vertex array. So the modern computers are very good at fetching, prefetching, getting right cache lines and get good performance. So this is not big deal. However, these other two accesses are the problematic cases because they are doing basically accesses all around memory with no locality presence. So they are the ones that we need to worry about. So to show you what's going on, I'm going to simulate it using basically simple cache by looking at this single access in here. And for simplicity, we'll assume our cache can only hold one cache line. And assume each cache line can hold two vertices, and vertex 0 and 1 goes to first cache line and 2 and 3 go to the next cache line. So now let's simulate this algorithm. The first thing what we have to do is vertex 0 needs to read from vertex 2, so that goes to the cache. So that's a cache miss in here. Then what we have to do is vertex 1 needs to read from vertex 0, so basically that goes to cache line in here. That I'll get a cache miss in here. Then basically vertex 1 read from vertex 2, so that goes to cache line in here. And then basically next time again what we have to do is vertex 0 has to go to the cache line, and every access basically incurs a cache line miss in here. There's only one cache hit comes in this computation in here. And so what you got was a system where we have very high cache miss rate. We only have one cache hit and 6 cache misses. So this is not that great. You're going to get pretty low performance. So what can we do here? So the problem is working set first is larger than the cache, and often only we use a part of the cache line. We get the entire cache line to utilize only one value to throw the rest away. And we want to come up with a transformation that will help in that. Basically, when working sets are larger than the cache, and in real world this is the case most of the time because we have normally working sets that could be 10 to 200 times larger than the cache size, so we can't expect the working set to fit in the cache. And often we only use a very small part of the cache line in here, perhaps 1/16 or 1/8 of the cache line being used when every time you bring the cache line, so that is not good. And in fact this is represented in the results we get. So if you look at this computation, the first blue part takes about 75% of the time because it has all these cache misses. The next part is very fast. So how to basically reduce this cycle? So we did a simple back of the envelope experiments. Basically what we did was we created the invalid program by accessing always the same value for rank and out degree. So the program doesn't work. But what we show here is that the minute you do that, the computation improved like 2.8x speed up, because now what you see is it's not the arithmetic operation that's basically keeping this, it is basically the cache misses that incurs for these indirect accesses. So we develop a technique that comes very close but almost 2x away from the best you can do when you have no indirect cache references basically. And let's first talk about these techniques. It's what we call frequency-based vertex reordering. The observation is cache lines are way underutilized, but certain vertices have much more likelihood of access than others, that if you can keep these things in the cache basically, then you can actually get much higher cache utilization. So what our design is, group together frequency access nodes and keep ordering the for the average degree nodes basically. So this is what we call frequency-based vertex reordering. So we look at out degrees, and there are two nodes that have very high out degrees, vertex 0 and vertex 3. So what we want to do is reorganize the cache. So by reordering these two nodes in here, and then we basically reorganize the data in here. Previously vertex 0, vertex 2, now vertex 0 and vertex 1 are in the same cache line. So now let's do the simulation again. So what you see is, to do this access, again a single cache line basically, you get a cache miss, and then you access the other one, you get a cache hit again, and then you get a cache miss to get vertex 2 and 3, and again a cache miss to get vertex 0 and 1, but it's being reused multiple times. And because of that, what you have is much better reuse. Instead of having 6 misses, we only have 3 misses, and we get a lot more hits in here. So it's much better cache utilization. So another thing we can do is cache partitioning. So what that means is partition the graph into subgraphs where random access is limited to the last level cache for each subgraph, and the porters each partition sequentially and merge the rank contributions for each partition at the end. So you look at this graph and you can partition these four edges to one graph and then the other edges to another graph, and then basically go iterate through graph by graph. So now we have 0 and 1 in one cache line, 2 and 3 in another cache line. So first we basically process this subgraph. So what that means is I am getting this cache line, and that's all I need to do, because I can basically use that cache line to update all these vertices, and then I switch to the next partition, and then I can basically first time I will get a cache miss, and then basically I am using the same cache line in here. So if you do that, we only have 2 cache misses when you switch partitions, and then we have a lot more cache hits in here. So this is even better than frequency-based reordering in here. So the previous example, if you do frequency-based reordering, you get about 35% cycle reduction. If you use partitioning only, you get 50% cycle reduction. If you do both together, we get about 60% cycle reduction. So this is really, really nice. So we are getting really good performance for PageRank. So have we solved the problem? Is this the solution for everything? So we were very excited and we used this optimization in breadth first search. Unfortunately, what we found was it actually slowed down. So the issue is optimizations don't always work across different algorithms and different data. So you have to really target these optimizations for algorithms and data. So the issue is there are many types of data, there's huge number of algorithms, and also there are different architectures. So this gives us a huge number of optimization combinations that we might have to do to get good performance. So this is really hard. This is where basically the GraphIt domain specific language and compiler comes in. So let me first motivate why we did GraphIt. So if you look at graph, there are many types of graphs. There are power law graphs where in World Wide Web or social networks there are few popular people that have millions of connections in here, and there are rest of people like us with very little connectivity. And these graphs have very different properties from, for example, bounded degree graphs, where something like a map or engineering mesh, basically each node has only few connections in there. There's a lot of locality in these connections in these graphs. So these graphs behave very differently when you want to get good performance. Then when you go to graph algorithms, again there's no one type of algorithm. For example, there are topology driven algorithms. So for example, something like recommendation engine or Google search, what you have to do is these algorithms go through, visit all the nodes and edges and do some processing in here. And then there's data driven algorithms. Basically we'll go starting with the data item and propagate to certain part of the graph. So for example, if you're trying to find a path between 2 locations in a very large map, you don't have to process the entire map, only data driven some nodes need to get processed in here. That's a very different type of processing you have to do. And then finally you have to run this on many different architecture, from CPU to GPU to modern domain specific hardware, something like MIT SOAM or distributed clusters. So each of these architectures you might have to do something differently. And there are many different things you can do. So for example, when you want to traverse, one way to do this push traversal. That means the value you want to propagate, you get the value and give it to everybody else. However, because I am updating all my neighbors, I might have to do, if we are doing this parallelly, I might have to do with some atomics. Basically, I can't just upgrade everybody because that means I might have race conditions. So upgrades might have to be done with atomics. But then I don't have any overhead. I am only updating the things I know that needs to have a new value, because I am the one who knows that the new value is different that I need to upgrade. But you can do a pull traversal where I basically read values from everybody and upgrade myself. Nice thing about that is I have no need to do any synchronization, but now I might be pulling values that haven't changed. So I might be doing a lot more upgrades than necessary. So there are choices like this. So another thing we can do is partition the graph. So if you partition the graph, you get a lot better locality because these graphs might fit in your cache. But now at the edges, you might have to do some extra computation. And also you might not have that much parallelism because now each partition might be small, so our parallelism has gone down. So what that means is if you're optimizing for these graph algorithms, it's a very difficult problem. You have to balance between three things. Balance between parallelism. That means you want to have just sufficient parallelism for your machine. You don't want to have too little parallelism to keep the machine idle, but you don't have too much parallelism that you can't take advantage. Then you need to get advantage of locality. So your memory system should be performing well all the time. That means you need to have data you are going to use in the memory system all the time. So you need to get good temporal and spatial locality. You really need to optimize for that. And then you need to do both by having good work efficient algorithms. Sometimes you can do extra work to get better parallelism, better locality, but if this extra work became too much, then you are paying too much of overhead cost. So for example, if you look at something like the push schedule, it stays somewhere between locality, parallelism and work efficiency. But if you look at the pull algorithm, it probably has a better locality and better parallelism but less work efficiency. And partitioning basically has a lot better locality but less parallelism and less work efficiency. So all these things fit in this space. So you have to navigate through this optimization space very carefully. So you have to look at the graph, the algorithm and architecture. So let me give you a couple of examples. So if you look at something like a page rank, you are basically working on a power law degree graph, something like a web graph, and you're running a topology driven algorithm on this thing in probably a large hardware, something like a cloud hardware system. And for that, the best thing might be a pull algorithm by partitioning and doing vertex parallelism in here. On the other hand, a different part of Google is trying to find directions. I am doing single source shortest path. I had to do something very different. Now I have a bounded degree graph. I am doing basically data driven algorithm on here. I might do push vertex parallel in here. The same thing in a GPU, I might tend to do edge parallel because I want to get a lot more parallelism for GPU than what the vertex parallelism might support. So what that means is we need to find the right set of optimization. Worse, if you don't find the right set of optimization, sometimes you can be 10 to 100x slower than what you could get in here. So this is critical to get these optimizations. This is where GraphIt came in. See, one thing GraphIt did was, as a dense language like Halide, it decoupled the algorithm from optimization. Algorithm says what to compute and optimization says how to compute that thing you want to compute. So we build a GraphIt DSL compile. It's easy to use because it improves productivity because you describe these algorithms in very high level format and also optimization in a very succinct way. But also it gives you really good performance. In general across many applications in many graphs in here because we can describe many different optimization depending on the criteria. And also I'll show we can get portability across basically GPUs and CPUs. So as I said, GraphIt DSL has algorithm representation and optimization representation. So let me describe them separately. So first look at the algorithms representation in GraphIt, the algorithm language. So we have different components for algorithm language. So for example, if you are doing algorithm that you are going to apply for all the edges, basically a topology driven algorithm, you can use this edge apply function and give this function that get applied to all the edges in here. On the other hand, if you are doing a data driven algorithm in here, what you can do is you can use these filter commands to filter from source and destination depending on the data and apply your function only to a selected subset of edges in here. And if you want to do vertex processing, we can also do that, apply for vertices. So now let's look at PageRank written in GraphIt. So first you need to have a function, this edge update function, that basically say each edge basically do this computation, basically find my neighbors and update my edge value using my neighbors. Note that I'm not saying whether I'm going to do it push or pull, just say what the computation in there. And then after that you have to do a vertex update function that basically calculate the new rank using the old rank and so on. And in the main, basically you do first this edge apply function followed by a vertex apply function. So here first do the edge apply function in here to do the near neighbor calculation, and then the vertex apply function to basically calculate the new rank and swap the old rank. So the next we have the scheduling language. So here's this algorithm again, and what we can do is we can say, hey, how to optimize this algorithm is provide a schedule. So the schedule says for this edge apply function that I have indicated using this S1 to sparse push. This will generate a piece of code that looks like this. But now, as you might want something a little bit different in here, I want to parallelize. So I just have to add this one line to my schedule that says do a dynamic vertex parallelism. Suddenly my generated code now has another loop that basically runs this thing parallelly. And basically also do atomic update, because we realize to run this basically push update parallel, you need to have atomic updates in here. So that's what it generated. But now instead of doing basically push, I want to do pull. I just change my schedule and suddenly my code is now very different. I have basically swapped the loopness in here and also got rid of this atomic, because I realized in order to do pull, I don't need to do atomic update. Now if you want to do something more fancy, something like optimize for NUMA, I can also add that for my schedule in here, and I get a NUMA parallelism. So if you keep doing this, what we are showing here is you get different speed up. So basically starting from schedule 1 with no parallelism, we can actually end up with about 20x speed up as we keep doing this optimization. So it's interesting. So even doing these small changes optimized, you can get really, really good performance. So there are many more optimization opportunities in GraphIt. So I have listed a few here. So what the GraphIt programmer has to do is write the algorithm and then play with these optimizations and see what happens, get some intuition, and basically after a few hours of trial and error, you can probably get a really fast program. So let me show you some results. So what we are showing here is some algorithms and graphs run over 7 platforms: LightGraph, GraphMat, GreenMall, Gaua, Gemini, and GrAPL. So what I'm showing here is right now what colored is basically already pre-drag on live journal graph. So 1 means you got the best performance. The rest of the numbers is how many times is off from the best performance. So basically LightGraph is about 3.48 times slower than the best performance in here. And Gaua is even worse. Whereas GrAPL is only 8% slower than the best performance within GraphIt. So that's only for one basically benchmark in one graph. But how about other graph? Things like the Twitter graph, web graph, road graph, and Friendster graph. So what we are showing here is even for the same applications, some systems do very well in certain types of graph but not so in the other graphs, because they have limited optimizations. Whereas GraphIt is doing pretty well. So now we'll go across different applications, both for search, connected component, on single source shortest path. What you see is this huge variety in here. Of course, for all the different systems, there are certain applications and certain type of graph they do really well, certain kernels, because they optimize for that. But also there are other types of kernels and sometimes other types of graphs that they're actually pretty bad, because the optimizations are not the right things for that. On the other hand, if you look at GraphIt, it actually do pretty well across the board, because we have the ability to basically run many different optimization combinations and find the right optimization for the right application, right graph, and get really good performance. And also, if you look at lines of code, which I'm not showing here, this is much less line of code than many other systems. Till now, we looked at topology and data-driven algorithms. However, all these algorithms, we process the active vertices in a random fashion, in any arbitrary order. What we realize is there are a lot of algorithms where this is not the right thing to do. You want to process the vertices in some very specific priority order. And if you do these algorithms, which are called ordered algorithms, you can actually get really good performance for these class of algorithms. So here I'm showing some performance improvements. So for single source shortest path and Keiko algorithms, if you do the ordered version, it can be 2 to 640 times faster than doing the unordered version. So let me show you how. Let's look at a simple algorithm doing single source sorted path, the Bellman-Ford algorithm or unsorted algorithm in here. Here the start node is marked in blue, and as we process, the final value is there, we mark it green, and the intermediate values are there, we'll mark it in red. And in the bottom line, we will update for each node the current distance we know. So we first start by looking at the neighbors of A, and both B and D we get numbers. And the next iteration round, we go and update the neighbors of B and D. You apply C, D, update E and F, but you realize D, E and F still don't have the final numbers. The next iteration round, the D gets its final number, and then it gets proprietary E and F and G. So if we do this thing right now, we did 5 rounds and did 10 updates. Now let's look at the same algorithm, delta stepping, basically doing ordered. In here, what we do is we use the delta value 10 for ordering. I'll explain this what's going on. So what happens is in here, the first you process B and D, and then you divide the distance by delta, and then you get first one basically get a value 0, and the next one will get a value 5, and they are in different bins or different priorities. So only the lowest priority things get executed. So then you go to B and do C, and again the lowest priority thing right now is C. Because of that, you do the neighbors of C, and then you update D, and now the lowest priority becomes D, and D update E and F, and E will update G. So now what we did was, compared to the previous time, we actually was able to do with only 7 updates get the results we wanted. So this is much faster doing here. And what we have done is done a trade-off between parallelism work efficiency. We have less parallelism, but it's a lot more work efficient because we visit only very few nodes. So in GraphIt, we can also handle priority-based extensions, and we have included this in both the language for algorithm and language for scheduling. So for language, for algorithms, there are a few keywords that we have introduced. So let's show how this is being used. So basically, to do delta stepping, you have to first define a priority queue, and then you initialize the priority queue, and then normal iteration, you see whether there's any nodes in the priority queue, and then you basically take the current highest priority vertices out there, and only that frontier get processed each iteration, and then you iterate and then you update the priorities. In the update edge function, basically what you do is we update the priorities given the current priority out there. So the next time around we'll have some new priorities. However, something very interesting is we hid the physical implementation of priority queue. There's nothing in this code that says exactly how the priority queues are accessed, except in a very high level interface in here. This gives us the ability to come up with different implementation that the scheduling language can choose. So again, let's see how this is done. And basically this is the algorithm part, and then we are writing the schedule in here, and in the schedule we said do a lazy update for the priority queue in here, and then we can generate this C++ code. Then if you want to do eager update, you can just change one word and you get a very different type of code in here. So let's look at how this is implemented. We are doing it using a bucketing implementation. What that means is the nodes are bucketed into their priority order, and then you go execute the lowest priority bucket first in here, and then basically they're doing global synchronization between going one priority after another. In the eager update, every time a priority change, the bucket is immediately updated. So this is faster when synchronization is a bottleneck in here, because you basically move things to the new bucket very fast. In the lazy updates, buffer this the newer priorities for a while and then do the updates later. This gets a redundant number of updates, because if you keep changing priorities, you don't want to always keep moving. But on the other hand, you might have more synchronization. Another interesting thing we introduced was bucket fusion. So sometimes there could be multiple buckets with same priorities. So if that's the case, you don't have to have a barrier. You can immediately go to the next priority without basically synchronizing between all the threads. So we have introduced bunch of scheduling language extensions to basically implement and choose between these optimizations. And this is very compatible with what we had shown before. And here's some results for this program. So what I'm showing here is basically 3 graph, live journal, Twitter and road graph in 4 different algorithms: single source versus sparse, PPSP, Keiko and set cover. And we are running it with this GraphIt, Julian and Gawa. And what we are showing here is Julian does not support eager bucket update. So when eager bucket update is needed, it's not getting good performance. And Gawa does not support strict priority ordering. So some algorithm that requires strict priority ordering, we could not get the correct result. So we couldn't do it with Gawa. And again, GraphIt, we can achieve constant high performance to get for across all these benchmarks and all the graphs. So I'm going to switch gears finally and look at hardware. So what hardware will give you the best performance for graph computation? It depends. So certain hardware, something like GPUs, have very good memory bandwidth and huge amount of compute power. However, CPUs have much larger caches, much bigger memory, and lot more out of order execution with things like branch prediction available. So what's the best hardware? So if you want to do a throughput oriented algorithm, so the GPUs will give good performance. Things like PageRAM, connected components, this is really good. Whereas algorithm that has little parallelism and with a very latency sensitive, things like SSSP and A-star, where CPUs can give you really good performance. So today, if you want to switch between CPU and GPU, basically you have to rewrite the entire application. We made a system where you just change the schedule and you can go between. And in fact, we introduced a lot of additional optimizations for GPU, because GPU things like load balancing is really important. And so we have additional optimization for GPU. So now GraphIt basically used to be you provide algorithm and schedule, and we also have auto tuner to basically find the schedule, and then you map for CPUs. But now basically with these extensions, we can go to CPU, GPU, and we are also looking at a lot of different domain specific architectures to generate code for. We did this by separating the compiler into 2 parts. So what happens is we have the front end of the compiler that do a lot of optimizations that are architecture independent, and then we generate a GraphIR, and then we build these separate backends, what we call graph virtual machines for each different architecture, that basically take the GraphIR, lower it to that architecture and do architecture specific optimizations and basically implement the code for that architecture. So right now I'm going to show you the results for a GPU backend. So again, we are showing for our GraphIt in here compared with Gunrock, G-Switch and SebGraph. Again, for many different graphs, for 4 different algorithms, what we are showing is GraphIt is getting consistently high performance. And this is very exciting because now we can go across architectures, And if you're a programmer, you only had to rewrite the schedule. Your algorithm you didn't have to touch to basically go between CPU and GPU. So you can try out between different architectures and see where you get good performance. So to summarize, what we have shown you here is graphs are very complicated and very diverse. They are diverse by algorithms, and differing on where you execute, there's a lot of diversity. But also, the graphs itself are very different. So you have things like road graphs that have a much more flat, a lot of locality, and then you have social networks graph that have very different structure with few nodes that has millions and millions of connections in here. And so if you want to optimize graph algorithms, you have to do many different optimizations, and depending on the graph shape and size, the algorithm and the hardware, that set of optimizations you have to do might be different. And what we have built is a system that basically has separated the algorithm side from the scheduling language. And in the scheduling language, we can basically select, or the programmer can select what set of optimizations you want. Because of that, we can get consistent, really high performance across a large class of algorithms and graphs. That's all I have for today, and thank you for listening to my talk. And when we have the live session, I'll be there, and if you have any questions, please come and ask. Thank you very much.